Welcome to The Explainer. Today, we're diving into a world where the rulebook we all know just gets tossed out the window. A world that's not science fiction, but the very bedrock of technologies that are going to change everything. We're talking about the quantum realm.
So, let's pull back the curtain and look at the fundamental principles that aren't as for textbooks anymore. Nope, they are building a new world of technology, right now, right before our eyes. So, to really wrap our heads around quantum tech, we first have to get that its rulebook is just different from the world we live in. It's kind of like this. Think about throwing a baseball. You know pretty much exactly where it's going to land, right? But with a single atom, well, all bets are off. Okay, so on one side, you've got classical physics. The stuff we see every day. A baseball in flight. It's predictable. Its path is set. That's our world. But then, on the other side, you dive way down to the atomic level, and that's where quantum mechanics takes over. Suddenly, things get weird. It's all about probabilities and possibilities. It's just strange. And you know what? It's exactly these weird, strange rules that give us this brand new, almost magical toolkit. So let's crack it open and see what's inside. All right, our first tool is a real mind bender. It's called superposition, and it basically takes the most fundamental rule of our computers, that something is either on or off, and just completely shatters it. Right, so every computer you ever used runs on bits, and a bit is simple. It's a 0 or it's a 1. That's it. But a quantum bit, what we call a qubit, oh, that's a whole different game. It can be a 0, it can be a 1, or, and this is the wild part, it can be both at the exact same time. Here's a great way to think about it. A normal computer bit, that's your standard light switch. It's on or it's off. Simple. But a qubit? That's more like a dimmer switch. It can be all the way off, all the way on, and literally every single shade in between, all at once. And that simple difference? It just explodes the amount of information you can work with. So what does this actually let us do? Well, because a qubit can hold so much more information, a quantum computer can explore a bajillion possibilities all at the same time. This is how they can solve certain problems that would take a normal supercomputer, the age of the universe to crack. And as a bonus, this incredible sensitivity also lets us build sensors that are just mind-bogglingly precise. Okay, so if one qubit can be in two states at once, what happens when you link a couple of them together? Well, that's where we get to our next tool. And trust me, this one introduces a connection that seems to completely defy the laws of space. This is entanglement. And yeah, it's as weird as it sounds. Imagine you have two particles that are linked. They're entangled. If you measure one and find out its state, you instantly know the state of its partner. And I mean instantly. It doesn't matter if it's right next to it or on the other side of the galaxy. It's this deep, mysterious connection that our everyday brains just aren't built to understand. But here's the thing. This bizarre, spooky connection is also an incredibly powerful tool. For one, it's the key to truly unhackable communication. Why? Because if anyone tries to peek at the message, they break that fragile entanglement link, and you know immediately that someone's listening in. It also lets us chain qubits together than a quantum computer, making them exponentially more powerful. All right, moving on, the next tool in our quantum box lets particles do something that, in our world, is flat out impossible. We're talking about walking through walls. Okay, think about it like this. In our world, if you roll a ball at a hill but don't give it enough of a push, what happens? It rolls right back down, right? It can't get over. But in the quantum world, well, because everything is about probability, there's a tiny but very real chance that the particle will just appear on the other side of the hill. If it ever went over it, it just tunneled through. And believe it or not, this isn't just some weird little quirk of physics. It's absolutely essential for actually building this stuff. It's the principle behind how superconducting qubits, the heart of many quantum computers, actually work. And it's what lets us make these quantum components smaller and smaller. Okay, so we've got these incredible tools, right? Superposition, entanglement, tunneling. It's an amazing kit. But like any powerful tool, you've got to know the rules of the game to use it. And here is maybe the biggest, strangest rule of all. The moment you try to look at a quantum system, you change it. It's wild. You have a qubit in that beautiful superposition of 0 and 1, but the second you measure it, it's forced to pick a side. It collapses into either a 0 or a 1. Now, this observer effect is a massive headache for engineers, but it's also a secret weapon. It's exactly why that quantum communication we talked about is so secure. The act of spying is the act of being caught.
So how do scientists actually control all this weirdness? Well, behind it all is some seriously deep and powerful math. It's the formal language that lets them grab the reins of these quantum systems. And it's this math that enables the mind-blowing quantum algorithms, the software that's going to solve problems our current supercomputers can't even dream of tackling. So, here's the most important takeaway. All the stuff we've been talking about, superposition, entanglement, tunneling, this isn't just theory on a blackboard anymore, not by a long shot. These are the actual real-world blueprints for technologies that are being built as we speak. Right now, in labs all over the world, brilliant people are making this happen. They're building qubits out of all sorts of things, like tiny electrical circuits cooled down to near absolute zero, or individual atoms trapped in laser beams, even single particles of light. Every method has its own pros and cons, but they all run on the exact same fundamental quantum rules. So think about the journey we just took. We went from the absolutely bizarre rules of the subatomic world all the way to a practical, revolutionary new toolkit for all of humanity. This is where physics stops being theoretical and starts becoming game-changing engineering. Look, the quantum revolution isn't something that's coming soon. It's here. It's happening now. We're learning to play by this completely new rulebook for reality. And that just leaves one big question. With these new rules, what impossible problems are we finally going to solve?